Diffusion, the international science radio show.
We have a bouncer on the doors of perception.
The good, the bad, the ugly.
It gets pretty exciting.
The myths, the truths.
Toxicology.
Astroseismology.
Magnetism. The dark side.
Genetically engineered potatoes.
Planetoid.
I
love that word.
Hello and welcome to Diffusion. Sit back and relax while we spin weird and wonderful science awarded directly into your ears. I'm Ian Woolf. On this edition, Sam Bladwell saves energy with Spintronics. First up, here are the 2019 Nobel Prizes for Chemistry and Physics. The 2019 Nobel Prize for Chemistry went to John B. Goodenough, M. Stanley Whittingham, and Akira Yoshino for the development of lithium batteries. Batteries are made from an anode, a cathode, and a medium in between, for passing electrically charged particles from the anode to the cathode. In the 1970s, Stanley Whittingham discovered that lithium is a very energy-rich material. He made a cathode from titanium disulfide, which, at a molecular level, has spaces that can house lithium ions. The battery's anode was partially made from metallic lithium, which has a strong drive to release electrons. This resulted in a battery that literally had great potential, just over 2 volts. However, metallic lithium is reactive and the battery was too explosive to be useful. In 1980, John Goodenough doubled the capacity of lithium batteries by demonstrating a cathode using a metal oxide instead of a metal sulfide. He demonstrated that cobalt oxide also has molecular spaces to house lithium atoms and can produce a potential of 4 volts. In 1985, Akira Yoshino used a petroleum coke anode with molecular space to house lithium ions to make the first commercial lithium battery, one that could be recharged hundreds of times. When the battery is being used, the lithium ions flow through the medium from the anode to the cathode. When the battery is recharged, lithium ions travel from the cathode to the anode. Unlike other rechargeable batteries, recharging doesn't break down the cathode or anode. Lithium batteries first went to market in 1991 and have changed the world. One half of the 2019 Nobel Prize in Physics went to James Peebles for theoretical discoveries in physical cosmology, and the other half went to Michael Mayer and Digi Kello for the discovery of the first exoplanet, a planet orbiting another star. Since the 1960s, James Peebles has made a lifetime of contributions to physical cosmology. What has become the standard model of cosmology, our understanding of the universe's history and nature. In the early 1970s, he was one of the first to run computer simulations of cosmic structure formation, a practice that is now an entire branch of research, where cosmologists explore toy universes. He predicted the detection of the cosmic microwave background that may be the echoes of the Big Bang. He explored the consequences for the growth of large-scale structures in the universe from the idea that our universe is dominated by unseen dark matter and dark energy that can account for the difference between our understanding of gravity and the movement of stars orbiting galactic centers. He contributed to our understanding of how galaxies form and how the elements form inside stars. He wrote the textbooks that cosmologists use today. In 1995, Michael Mayer and Digi Kello announced the first discovery of a planet outside our solar system, an exoplanet orbiting a star in our home galaxy, the Milky Way. At the Haute-Provence Observatory in southern France, they were able to see planet 51 Pegasi b, a gaseous ball comparable with the solar system's biggest gas giant, Jupiter. Over 4,000 exoplanets have since been found in the Milky Way, with an incredible wealth of sizes, forms and orbits that challenge our understanding of planetary formation. The 2019 Nobel Prize for Medicine or Physiology went to William G. Kaelin Jr., Sir Peter J. Ratcliffe and Greg L. Semenza for discovering how cells sense and adapt to the availability or lack of oxygen. The big Nobel controversy is that not only have few women in history been awarded a Nobel Prize, but that in 2019 not a single Nobel Prize went to a woman. With all the amazing work that's been done in the last 60 odd years that covers the 2019 winner's work, surely at least one woman's work was worthy of awarding a Nobel Prize? You're listening to Ian Woolf on Diffusion Science Radio. Send emails to science@diffusionradio.com. We're brought to you across Australia on the Community Radio Network and podcast over the internet on www.diffusionradio.com. Spintronics. Sam Bladwell is a theoretical physicist at the University of New South Wales where he studies condensed matter theory in the Fleet Group, FLEET. He was fresh from an international flight and still very jet-lagged, as you can hear in his voice. I began by asking him, what does FLEET, FLEET, stand for?
FLEET stands for Future Low Energy Electron Technologies. It's one of the ARC Centres of Excellence. All ARC Centres of Excellence, it seems, need to have an acronym which stands for some particular word.
And what's ARC?
ARC is the Australian Research Council.
Right, so it's a Centre for Excellence, and it's to do with low energy electronics. But what do you do to get lower energy electronics? And I understand it's also not just lower energy, but faster.
It's kind of both, but maybe we should backtrack first and start off with why you want lower energy electronics. So chances are if you're listening to this podcast, you're on an iPhone or something like this, or maybe you're at your computer. But the podcast itself is stored somewhere in a data center somewhere around the world. And there's actually many of these data centers, in the United States, in Australia, in Iceland, all over the world. And these data centers store all of the bits of information which are then distributed out on the various requests that we have, whether it be to watch a YouTube video or to listen to a podcast like this. And so whenever you do this, you're calling out this request and you have a whole bank of computers that has to run to distribute this out to you. And in this process, you actually use a lot of energy. So these data centers now use about 10% of electricity globally. And the reason for this comes back to the design of the computer itself, or the design of one individual component of the computer, the transistor. Basically, the design hasn't really changed for 70 years or so. When it was first discovered in 1947, it hasn't really evolved that much since then. I mean, obviously it's gotten significantly smaller, but it hasn't changed sufficiently in terms of energy usage.
So we're using the transistors that were designed way back when, so 70 years ago, only enormously smaller, so we can fit lots of them onto a chip, but it's basically the same design. So just roughly, what is the design of a transistor?
So a transistor, I should go back and explain what a transistor actually is, because it's probably not obvious for people outside of physics or electrical engineering and stuff. But a transistor is basically like a little valve. You can think about it kind of like a tap that you have at home, which is connected up to the water mains, right? And you can turn that tap on and off using the little valve at the top, and that will control the flow of water. And a transistor is the same basic idea. You have a gate, which is like the little tap, and then you have a pipe which contains the electrons or the electron current. And basically you can switch it on and off using the gate. To understand why this is useful, just think about the way you could encode information in this, right? You can have a state where electrons are flowing and a state where they aren't flowing. And if you write these down as being your 1 and your 0, you can start talking about doing logic operations using this, using various combinations of transistors.
And so you're looking at newer and better designs that might be lower power to do the job of a transistor?
Yeah, to come back to it, part of the issue with the traditional transistor design is that when you perform this switching procedure, when you're switching it on or off, you have to use quite a bit of energy. And so there's two major issues that come with this. Firstly, you waste energy doing the procedure. And the second point is that when you're wasting energy, you generate heat, okay? And if you generate heat and you have a lot of transistors, so each transistor only generates a very small amount of heat because it's, nanometers across. But if you have a lot of them, billions of them are in a computer chip, and then you've got many, many computer chips in a data center, you generate a lot of heat. And if you generate a lot of heat, you need a lot of air conditioning to cool the center down. So the two major reasons why these data centers use so much electricity is because they have to be cooled down, and they also need a lot of energy or electricity for the actual computation itself.
And we're only using more and more and more computing power and storage for everything as the internet eats all machines and all industries. So are we going to reach a point where we're just got too much heat for us to do any more with the machines?
Well, I mean, there's ultimately it's part of that is a question of economics, right? It's whether it's economically viable to do this. And you can look back at past industries and past industrial transformations and say, for instance, with steam engines, right? When steam engines were first developed by Thomas Newcomb, they were particularly inefficient and they weren't used for much except for pumping water out of coal shafts. Then, of course, James Watt came along and drastically improved the efficiency, and so they could go from being just used in coal shafts in, Cornwall, wherever they were first used, to being used in a whole lot of industries. And then as the cost of this went down, the amount of fuel you had to use, so it could be applied to more industries still. And a similar thing is, I'd say, likely to occur because, of course, there's many things that we do now, or we're starting to do a lot more of, that require huge amounts of computational power. So, obviously, in Fleet, we're interested in things like data centers and such. But more generally, you could look at say AI, which to train a neural net requires a huge number of what we call GPUs or graphics processing units, and a huge amount of computing hours. And this ultimately translates to a huge amount of energy or electricity. So whenever you're using Google Translate or something like this, there's actually a lot of electricity and energy that goes into doing that kind of machine translation procedure. And if you start to talk about, say, AI taking over entire industries, the amount of electricity that you require to do this would be actually quite large.
So we need to reduce the power requirements by quite a bit if we're to keep going the way we're going.
Yeah, I mean, it's a tough question to make a definitive statement on it, because ultimately we still can generate more electricity as well. But I think it's an important thing, particularly considering the fact that we're moving towards a world where we have to be much more careful about how we generate power, given the looming climate crisis that we're facing. It's the ability to continue to push forward with this kind of digital transformation and computational transformation, which I'd say is only partly done, right? That requires a significant improvement in the efficiency of computation itself. And it's maybe worthwhile just pointing out that when we talk about efficiency, right, we're referring to comparing it to, say, the thermodynamic efficiency. And the thermodynamic efficiency can be understood as the best you could ever do. So if you're, say, looking at a car engine, there would be some optimal car engine that would work as efficiently as any car engine ever could, and will generate the maximum amount of rotational motion of, the crankshaft for the fuel that you put in. And current car engines can only get to like 30 or 40% of that, as far as I understand. Now, for computers, you can talk about a similar thing, which is like, how efficiently could you do computation? Like, what is the best possible computer you can make, or the best possible transistor you can make to switch? And there's a limit on this, because, the Landau limit of computational cost. But it's, the amount of energy required for this, perfect thermodynamic one that satisfies this limit is, 1,000,000 times better than a current transistor.
So there's lots of room for improvement.
Yeah, there's a huge amount of room for improvement. And the real, like, at least a part of the question is, can you make a significantly better transistor? But then also there's a second industrial question, which is, well, if you can make a much better transistor, can you make it in a way that is competitive industrially with silicon, which is another question entirely and kind of a bit beyond fleet.
So what sort of processes are you looking at to make these lower energy, more efficient devices? Because I know you're not just using simple semiconductors like silicon that we've been using for the last 70 years. You're looking at different materials and different physical processes, I believe.
There are quite a few different materials that we look at. So for my own research, I mainly focus on spintronics, or what we call spin-based electronics. And the idea here is that for an electron, it'll have two quantum states, spin up and spin down. And you can encode your 1 and your 0 on this. And so the idea is to use spin rather than charge to do computation or to encode this kind of information. And it's important to realize that this isn't quantum computation. You're still doing classical computation. It's still 1s and 0s. And there's no quantum gates or quantum operations. But you're using quantum mechanics to obtain an improvement in the efficiency of the computer or of the transistor.
And what sort of materials do you need to have spin electronics?
So you need a material with a large spin-orbit interaction, which is part of the reason why silicon isn't that good. But there are many materials that do have large spin-orbit interactions. So topological insulators are one particular example, but mostly I work in close collaboration with experimentalists who use a material called gallium arsenide, which in itself doesn't have a particularly large spin-orbit interaction for electron systems, but you can do certain things to make it large for holes, which you can think about as being like a weird quasi-particle where you've removed an electron and the gap left over from the electron not being there is the thing that you're actually moving around. Think about it like if you're in a stadium and everyone decides to shift over a seat, right? The empty seat will propagate in the other direction. The best way to think about it is that it's like a bubble in water, right? Obviously, things normally fall to Earth, right? Because, there's a gravitational field, but a bubble is effectively a quasi-particle and will move in the other direction. And it'll have some associated kind of mass in relation to how quickly it moves up, which won't be the same as like the material that's been taken away. So a hole is similar to this.
So a hole is almost like a bubble within the electrons.
A hole is a bubble within the electron sea. It's the best way to think about it.
Fantastic. And you mentioned a topological insulator. Now, topology is to do with the shapes of things?
It's probably worthwhile saying this is being a physicist and being a centre of physicists. We probably use topology in ways that mathematicians wouldn't approve of. But the characteristic feature of topological insulators and most of these systems, also the quantum Hall effect and stuff, is that it's very robust to changes in the material. So you can imagine for the quantum Hall effect, which is simpler, it just has electrons flowing around the outside of the sample and no electrons moving in the middle. So this is done using a magnetic field and is used a lot in metrology, so generating very, very accurate measurements of things. So one of the things they're doing now is redefining the kilogram, etc., the basic units on the basis of the quantum Hall effect and the Josephson effect and things like this. But this is a digression.
You've got a material where the electrons can travel around the outside but not through the middle.
Yeah, so basically the key point about a topological insulator, why they're interesting, is because the bulk of the material, if you imagine you've got a cube or something like this, the bulk of the material is insulating. So there's no electrons that can move at all, but the surface of the material can have electronic states.
And what sort of electronic states do they have? So is this a material that acts as an insulator, or can you make it be better conducting?
So the key point here is that the states on the surface are conducting states. So it's a conductor on the surface, but in the bulk it's insulating. And the really nice point about this, particularly when it's in 2 dimensions rather than in 3 dimensions, is that the states have to travel in a particular direction. So you can have what we call a 2-dimensional topological insulator, which is the quantum spin Hall effect, for instance. electron states of a particular spin will only move in one direction. So the main thing to remember with a normal metal or something is that if you're passing current through it, the electron states can scatter, okay? Which is basically just the electrons are moving in a particular direction, they hit something, and they tend to bounce backwards or sideways, okay? In this process, you actually generate heat eventually, and this is one of the major issues that you have with say just moving current in an ordinary metal. In some particular conductor, you'll generate a lot of heat if you have a lot of current. In a topological insulator, in a two-dimensional topological insulator, or in the quantum Hall effect, the number of ways in which scattering can occur, the number of ways in which electrons can be knocked backwards, is significantly reduced. In the case of the quantum spin Hall effect, you have edge states, like these boundary states, these conducting channels at the edge of it, which are spin polarized. So spin up states, one of the quantum states I talked about earlier, it will only go in one direction. The other quantum state will only go in the other direction. And if there's no mechanism for these two states to be coupled together, like if there's no way for a spin up to become a spin down, there's no way for that spin up state to scatter backwards. So as a result, you don't have any dissipation. So you can put some current into this edge channel, and it'll flow along without dissipating.
Terrific. So it's a way of getting conduction going without obstacles, without using superconductors.
Yeah, obviously it's quite a different thing to superconductivity, and you can't transport the same amount of electricity. So it's to some extent it's quite different. In other ways it's fairly similar, right? At the end of the day, a superconductor is such a good conductor because ultimately scattering is strongly suppressed. So there's similarities and there's differences there.
And do these topological insulators with the edge conduction, do they need refrigeration?
At the moment, as far as I'm aware, all of these are the gap, like the gap between the size of the gap in the insulating state. So for all topological insulators, as far as I know of, the gap, so actually I'll have to explain gap, won't I? So you have a semiconducting gap, right, or like some type of bulk gap that you're connecting. And if this gap is smaller than the thermal energy, then right, it ceases to be a topological insulator because ultimately electrons can just jump up and get away.
It's the working temperature.
Yeah, so the working temperature of all of these is, I'd say, significantly less than room temperature as it currently stands. But of course it depends on the material, and they're constantly finding new materials. And I have to admit I'm not at the forefront of my knowledge of the various materials that are being used.
So with the ones you know about that are being the experimentalists are playing with, they currently need to chill them down, but perhaps, do you think not as much as the superconductors need to be?
Well, superconductors now work at pretty high temperature as well, so I'm not sure what the comparison would be. But I'd say the usage here is very different. With the superconductor, people normally talk about it, the huge societal benefits is coming from being able to transport electricity very efficiently. Whereas for these spin-based devices and stuff that we're talking about, or topological insulators, most of the usages that are being described are related to things that don't require huge amounts of current to be moved around. So you're not talking about transferring vast quantities of renewable energy from a desert to somewhere else in the world or something like this, which people have proposed. For superconductors, instead it's much more, you don't have any dissipation for some particular electronic device, which would use a very, very small amount of current. A very small amount of current, typically very low voltages as well. So it's got quite a different application area. Coming back to this point about reaching an energy crunch, right? As I said, it's not we'll reach a point where we just can't do this anymore. It's more that if we talk about, things becoming even more ubiquitous, like more devices being connected, more data being generated, and particularly like the use of AI and stuff for various new technologies, all of these things require more computational power. And so roughly every decade we double the amount of electricity we use in these data centers. I mean, the big point here with all of these things is that you're trying to get to a point where we can actually use computers for more than we currently do. And to do this, we have to design computers, and particularly like these large data centers and such, to use significantly less electricity. This also for other things too, like blockchain, for instance. One of the major issues with Bitcoin was the amount of electricity that it was using to verify transactions. So for a lot of technologies that are kind of in their early stages at the moment, they're really reliant on computational power, and if they're really reliant on computational power, if they're expanded up to cover the entire globe and, become as common as, some futurists talk about them being, we're going to run into a huge issue with the amount of electricity that the computers that will make up those systems are going to use if we don't significantly improve the efficiency of computation.
Sam Bladwell, thank you very much.
Thank you for having me.
That was Sam Bladwell working on future low-energy electronic technologies in the School of Physics at the University of New South Wales. Sam will be back with more Spintronics soon. And that's all from us this week on Diffusion. Are you a scientist, artist, biohacker or maker who'd like to be interviewed about your work? Would your company like to sponsor Diffusion? Send your contributions, opinions, helpful suggestions and donations to science@diffusionradio.com. That's science@diffusionradio.com. Please like the Diffusion Science Radio page on Facebook and rate the show on iTunes. Tell your friends. Follow me on Twitter @Ian Woolf. The news music was Rhinos Theme by Kevin MacLeod of Incompetech.com. I produce Diffusion, which is broadcast around Australia to 28 stations on the Community Radio Network, including 2RBM in the Blue Mountains of New South Wales, 8CCC in Alice Springs and Tennant Creek, 2MVR in Nambucca Valley, 3MBR in the Mallee Border districts of Victoria and South Australia, City Park Radio 7LTN in Launceston, Tasmania, 2XXFM in Canberra, and my local station, 2RDJ in Burwood, New South Wales. Diffusion is syndicated globally on the National Science Foundation's Science 360 internet radio station and also on astronomy.fm. Subscribe to the podcast on the Diffusion website, www.diffusionradio.com. That's www.diffusionradio.com, and check the website for links, photos and videos about this week's show. If you enjoyed the show, you can explore more than 950 previous episodes archived on diffusionradio.com, where the shows are labelled by keywords so you can focus in on the stories you want to hear. Join my patrons at patreon.com/diffusionradio. Make a donation through paypal.me/IanWolf. Subscribe to the Diffusion YouTube channel at youtube.com/c/diffusionradio. I'm Ian Woolf. Join us inside your audio device of choice for more science wondering next week on Diffusion Science Radio.
Science is fun. It helps you to learn, to know, and to appreciate. When you study science, you may go on field trips. You discover the marvelous interrelationships between all living things. You learn to read the history of the Earth as it is written in rocks and fossils. You find out what makes things tick, everything from a molecule to a living organism. In the study of science is found the most useful and satisfying knowledge of man. Knowledge of his physical world, its past, its present, and its future. And in your moments of relaxation, now and in the years to come, you will find the study of science leading you into fascinating pursuits: photography, collecting. Why study science? Study science because you will find in the study of science a richer, more rewarding life.